Now we're going to move on to a more advanced way of modeling our rolls. In the previous example, we used rand between to get random numbers between 1 and 6. And so that implicitly assumes that 1, 2, 3, 4, 5, and 6 are all equally likely. Now that's not always what we're going to want. If we work with alternative distributions or we put some weighting on these die to make some numbers more likely than others, we want to be able to model that more flexibly. So the way we're going to do this is kind of through a several step process, but the key piece we're going to need from the randomization side is the rand function. So notice we could do rand between, or we could just do rand. So what does that give us? It gives us a random number, a decimal number, somewhere between 0 and 1. And we can actually see that it's a very precise number. If we add lots of decimal points, we can actually see it get bigger and bigger there. So let's actually unwind that. And so we can see that that random number is also changing. So it's drawing what is a uniformly distributed random number between 0 and 1. So it's equally likely to be anywhere between 0 and 1 versus like a normal distribution where outcomes are more likely to come towards the middle of the distribution. This is uniform, so it's just as likely to be near 0 or 1 or at 0.5 in the middle there. So that uniform random number now, we can use that to translate into dice rolls. And that's what I'm going to show you before we actually start adding any tilt. And so the way we can think about this is if we think about 1 through 6 as our different values, we can say that the probability of each roll is 1/6. Right? 1 out of 6 outcomes, so each one's about 17% likely. Now what we importantly have to do is create a cumulative density function, or CDF. And what that's going to do is allow us to look up this random value, in this case 0.98103, in that set of random, in a CDF function to determine which number a given random number equates to. For example, we could think about splitting up the line from 0 to 1 into 6 different buckets. So anything that's between 0 and 1/6 counts as a roll of 1. Anything between 1/6 and 2/6 counts as a roll of 2. We're just operationalizing that by using this probability column and the cumulative density function. So for the cumulative density function, we're going to start with a 0 value in our first cell, and then we're going to sum up all the probabilities up to that point. So we're going to sum up, in this case, F3 to F3. So we're going to the prior cell. And as we drag this down, what we get is the probability of an outcome ending up at that value or lower. So essentially, anything that ends up between 0.67 and 0.83, that's kind of in that 5/6 bucket, is going to get translated to a 5. Anything above 0.83 is going to be a 6. Anything between 0 and 0.17, that's going to translate here to our number 1. All right, so we can use something like a match function with ascending matching to make that happen. All right, so let's see what that looks like before we go too much further. So I'm going to first pull 2 random numbers. Notice that they're always going to be changing every time anything changes in the spreadsheet. And now we got to translate that random number into our roll. So I was proposing we use the match function. So we can use match. Our lookup array is going to be that cumulative density function. We're going to use ascending matching, which is the less than matching. And so what we should see is in this case, we get the first number. 0.015 matches to this. It's less than 0.17, so it goes back to this first row. If we drag this across, making sure we lock our array up there, we can get our second roll, which 0.183 should end up between 0.17 and 0.33, so it translates to a 2 in our dice roll. All right, so we've built our basic rand between, we've just done it in a more complicated fashion. The reason we did that, though, is because of the flexibility it allows. So let's just finish this off real quick. I'm going to flip back and steal our sum function we wrote before, or our win function, rather. And now we have the basic model constructed. Now we want to add that flexibility of putting a little tilt on this game. All right, over here at the top, I have a weighting, and then the numbers, the dice that we're going to weight. So for example, we could weight dice 3, 4, and 5, or the rolls 3, 4, and 5, and make them more likely, and make 1, 2, and 6 less likely. Or we can change it to 1, 2, and 3, make those more likely, and 4, 5, and 6 less likely. All right, so how do we do that? So what we're going to do is we're going to add some bit of weight. Let's just say 5% weighting to 1, 2, and 3. So the way we can do that is we can come into our formula and check to see if that number 1 is in our list of things we want to add weight to. The way we can do that is with a VLOOKUP, or you can think about an XLOOKUP or a match, either way. What I'm going to use, though, is the is error, because what we recognize is that we only have 3 numbers there. So if it's a number that's found, we want to increase the probability of that number. If it's not in that list and thus gives an error message, then we want to actually decrease the probability. So we're going to give a little bit of weight to some numbers and take that weight away from the other numbers. All right, let's see what happens here. So we're going to do an is error to VLOOKUP that number 1 in our array of numbers, locking that. We just want that same column back with an exact match, so we're using false. Now, if that's an error, right, if it is actually an error and that's true, then we want to subtract off that fixed weighting, whatever that shift is going to be. Otherwise, we want to add it. So then we'll lock it'll be positive there, and we hit enter. And we see that we got 21% now on the probability of a 1. Notice that that updated our CDF and shifted that as well. However, notice that we also have more than 100% probability. We can't have that with a probability distribution, so let's make sure we fix that. Good. We see that we increased the probability of 1, 2, and 3 and decreased it for 4, 5, and 6. If we want to, we can actually come in here and change these to 4, 5, and 6 and flip it. So now we have more weight on 4, 5, and 6 and less on 1, 2, and 3. We can also change the weightings. Let's make 10% more weight. So now we're really heavily weighted die. Or you can just do a very small weighting to where it's just a little more likely some numbers come up more often than others. All right, so we have our weight built in. Let's just start with a non-weighted die to build up some intuition. But then we know we have this capability built in there. And importantly, whatever these probabilities are, our CDF always updates. That's the key piece for getting our random numbers back out, or our rolls, is that we're using this CDF, which is calculated based on the probability of each different outcome. So whether you're doing this with dice rolls or with interest rate movements, it doesn't matter. You're still going to build a CDF and translate that CDF into random outcomes based on how the different probabilities add up. So that's really the key piece to getting any probability distribution and translating your rand number from Excel into the outcomes you're interested in. All right, so now that we have this built, let's look at the first way that we can actually build a Monte Carlo simulator. So the first way is really just to take this model. Here's our model, right? Very loosely speaking, we have 2 random numbers, we translate those into our rolls, and we have our outcomes. And we can just create 1,000 copies of this model. This is not always going to be feasible, right? This is a very simple model we can do in 6 cells. And it's going to be easy for us to then just copy this down over 1,000 cells. Again, bigger models, this is not really going to be feasible, but for now we can do this. And what we can see now is that we can summarize the outcomes. I built this ahead of time, but I'm essentially adding up the number of wins, the number of losses, the number of draws, how many 12s show up. That actually is based on the wrong column, so we need to fix that real quick. We see our winnings and our expected value. So what all does this mean? This means on average, if you bet $1 on this game, you on average are going to lose about 7 cents of that dollar. So this game is not a good bet, which we kind of knew from the start, since we took that 12, which would be a winner normally for the player, and we flipped that towards the house. So we built the edge in for the house or the casino, and that's where that shows up here, is that expected value shifts. On the other hand, we can now say, what if we put some extra weight on 4, 5, and 6? Let's put a little bit more weight on 4, 5, and 6, and what happens? Bigger numbers are more likely, and now our expected winnings go up to 23 cents. Now before we go on, notice that 2 is a random outcome. We're only doing 1,000 trials, which is not that many in the grand scheme of things. So if I update everything by hitting F9, we're going to notice that the whole spreadsheet updates, and now our expected value changed as well. So we have to keep that in mind, that 1,000 trials is a lot, but it's really not a lot when we're trying to deal with a bunch of randomness. So doing 10,000 or 100,000 or 1,000,000 trials, will give you a more precise estimate of what that mean is or what the distribution looks like as well. But that obviously takes more time, more computational power, which sometimes in Excel can actually be some pretty heavy lifting.